I'm not sure if you are going to hear me well today. So if you cannot catch something, just let me know and I will try to repeat it. So the thing is that today we are starting the second part of modified gravity, and it's about what is called the Einstein mechanism. And but for that, I have first to complete something that we started at the beginning, that the action in general relativity is not well defined. So we have to add a term which is called the Gibbons-Hawking term. And this term will turn out to be very important when we are talking about the extra dimension. So all the point for the moment is to talk about what is called the Gibbons-Hawking term. So this term is, you have to take it not as something for modified gravity. It is something fundamental in general relativity. For just the equations of motion, most of the time people don't care about it, but you should care about it if you want to have a mathematically well-posed problem. Secondly, it becomes very important as soon as you are starting looking to the border of the space-time, and this can be the horizon of a black hole or the asymptotic behavior in the ADS, for example, all these ideas of ADS-CFT. So the idea is very simple. Imagine I will start with a simple example in order to understand it, and then we generalize it to GR. So the simple example is the following. I'm just taking something in classical mechanics. So I'm taking an action which has this form. So the action is a Lagrangian, the integral from T1 to T2, and the Lagrangian, I will take something which is a Q double dot. So I'm taking a very, very simple Lagrangian. Q is some variable, and we have we have a Lagrangian where there is a second derivative. So imagine I would like to do the variation of this action. So if I make a variation of this action with respect to the parameter Q, what am I going to get? The first one, I'm getting delta Q, Q double dot, and then I have plus Q, delta Q double dot. So far is fine. This is what we get. And what we want to do is to do some integration by parts in order to have a delta Q. So how to do that? I just have to say that Q delta Q, Q delta Q double dot is actually equal to Q double dot delta Q plus some total derivative. So if you take the derivative of that, you will get Q dot delta Q dot minus Q dot delta Q dot. That goes away. Q double dot Q delta Q double dot is what we want, minus Q double dot delta Q simplifies with this one. So we have equality here. Okay, fine. So in this, finally what we have is the following. The integral dt, this term plus this term is twice, but we have total derivative. Okay, so assuming that the variation of the action is 0, usually what we say is that that will be the equation of motion. Means that Q double dot is equal to 0. But to do this, actually, we have a boundary term here. This boundary term is a q delta q dot minus q dot delta q that we evaluate between T1 and T2. So what is the problem? The problem is we have two types of boundary condition. When we do the variation of an action, I can consider that delta q at T1 and delta q at T2 is equal to 0. So I fix my boundary conditions. This is the standard boundary conditions. They are called Dirichlet boundary conditions. This is when I say that delta q is equal to 0. Remember that we have a second order differential equation. I impose two conditions, so my problem is well defined. The other one is the Neumann boundary conditions, where I impose that the velocity is fixed. Okay, and if I fix that also, I fix the velocity in both extremes, then I have a well-posed mathematical problem. The problem here is that I have to fix delta q dot in T2 and delta q dot in T1 to be 0, and I have to impose delta q in T2 and delta q in T1 to be 0. So I have to impose 4 boundary conditions. For a second order differential equation, that is too much. I'm putting too much constraints on my system. So it's true that most of the time we just say, oh, this is a boundary term, we don't care, and we don't look at it. But actually it's very important. So we cannot actually conclude with that. The problem is not well defined. What we have to do is to add in our Lagrangian some term which is going to take care of one of these two, in order to have that we have a second order differential equation with only 2 boundary conditions and not 4. Okay? You have questions about that? Comments?
So,
yes?
So how could be a Lagrangian a function of q double dot?
It's possible, why not? The Lagrangian can be a function. It's true that when we start working in the simple examples, we always give this, q dot. But it can be a function of q double dot, q triple dot, whatever we want. And general relativity, this is why it is important in general relativity. The Lagrangian in general relativity, the variable is the metric. But we have first derivatives of the metric. And we have also second derivatives of the metric in the action of general relativity. This is the curvature scalar R. The curvature scalar has derivatives of the Christoffel symbols. The Christoffel symbol has one derivative. So at the end you have 2 derivatives. So we are exactly in the same situation. Even if we have second derivatives, the equation of motion is still second order. Because if you take an action of this form, for example, then you will have a 4th order differential equation. So then it's a completely different theory. This is what we have usually in modified gravity. But this is the analog of general relativity. We have second order derivatives, but the equation is still second order. And the same way than GR, this will bring something that we will have to impose too many conditions on the boundary to have a well-posed problem. Okay. So how to solve this problem? To solve the problem, we have to add actually some boundary term which is going to take care of one of these two terms without changing at all the physics, in the sense without changing at all the equation of motion that we are going to have at the end. So this is what I'm going to do. So what we are going to do is to add, we add a term which has the following form, which is minus d dt q dot. I can always add to a Lagrangian a term which is a total derivative, and it will never change my equations of motion. So I can add something like that. I will still have the same theory. But now I will have a well-posed problem. So what is my new Lagrangian? My new action is the initial Lagrangian, q double dot, minus this. Now if I do the calculations of that, I will get minus q dot squared and minus q double dot, which is going to cancel. So I have just minus q dot squared. Okay, so what I'm saying is that this action is exactly equivalent to this one. There is just a boundary term between them. But now, with this one, I don't have any more second derivatives. So I know that the action will be well defined. So if I do the variation of that, I will get a minus 2 integral dt q dot delta q dot. Okay, I have to do an integration by part, but of course taking into account that there is a total derivative. So what is this? This is equal to d dt of q dot delta q minus q double dot delta q. So concluding on that, now I have a variation of the action which is minus 2 times this minus is 2, the integral dt q double dot delta q, and then I have this boundary term is minus 2 q dot delta q that I have to take between t1 and t2. Now if I use Dirichlet boundary conditions, this is going just to be 0. I can fix it, and then the variation of the action tells me that q double dot is equal to 0. Okay, and now I have a mathematical well-posed problem. So the first thing was we had a problem because second derivatives, they appear in this Lagrangian, but they appear linearly. This is a very important thing. We don't have things like q double dot squared. This will provide a complete different theory, which is going to be fourth order, etc. But we have just a linear second derivative, and we know that in this case we will not have a well-posed problem because there are these two things here that we cannot impose at the same time. So we add a boundary term, something like that. And this boundary term takes care of one of these terms and makes the problem well-posed. Okay? So we are going to do the same thing with GR. In GR, we have also second derivatives. They appear also linearly because the curvature scalar R contains second derivatives, but it contains it in a linear way. If you are looking to a modified gravity theory, like an R squared, as we saw yesterday, we will get something like that. So we will get a fourth order differential equation, not second order. That will be completely different. Okay? So the main thing now is to see what is the term to add in GR. And this is called the Gibbons Hawking term. It has been derived by them, by Hawking and Gibbons, quite some time ago now. Okay, questions? Comments? Okay, so let me show how to do it in GR. But for that, as you can see, we have to add a boundary term. Here, boundary is in some sense very easy because the only variable or coordinate is time. So it's a boundary in time. Here we are talking about space-time. So we have to define a boundary in space-time, which is a three-dimensional surface. So we have our four-dimensional space-time, and the boundary is three-dimensional. So it's a hypersurface. So we have to discuss a bit about what it means, a hypersurface, how to define the geometry of a hypersurface, and from that, we will be able to define the Gibbons-Hawking term. So there is two parts. One is that I will explain the geometry of hypersurfaces for the ones who don't know well about it. And then after that, the calculation, it's just in my notes, so I will not reproduce it actually. So first of all, how do we define things for a hypersurface? So imagine that you have any form of hypersurface here. So this is going to be the boundary of my space-time. There is a hypersurface here, and this is going to be the full space-time. And I will fix my boundaries on these hypersurfaces. So just for notations, I will define the full space-time here with some coordinates x mu, and I will call this space-time M. And this hypersurface, I will put some coordinates on it, which I will call y. And this hypersurface, usually we write it as sigma. Okay. So M is equipped with some coordinates x mu, and sigma is equipped with some coordinates y. How do we define the equation of the hypersurface? The equation of a hypersurface is something which is a constraint on the coordinates x mu, any form of constraint. Let me give an example. If you take a hypersurface which is just the surface of a sphere, what is the equation? The equation of this surface okay, so this is my constraint on the coordinates. So this is just what I'm writing here. It's some constraint on all the coordinates which defines a hypersurface. So this is one way to see it. The second way to define the equation of a hypersurface is in a parametric form. So you have also the parametric form, which says that the coordinates x mu are defined with respect to the coordinates of the hypersurface. For a sphere, it is, example again, for the sphere, you have that x is r sine theta cos phi, y is r sine theta sine phi, and z is r cos theta. So you define that these coordinates in the full space are written as coordinates of the hypersurface, which are the coordinates theta phi. So this is the parametric form. So you have two ways to define an equation. Is there either just a constraint on the coordinates of the full space-time, or in a parametric way, you say that these coordinates are functions of the coordinates of the hypersurface. So this is going to be the second way to define this. Okay, so now that we have a hypersurface, what I would like to define is actually a normal vector to this hypersurface. So I would like to define a vector which is normal to it. How to define it? Actually, it is just the gradient of the constraint that we had. So n mu, the normal vector to sigma is proportional to the gradient of the constraint equation. This is how you define a normal vector. So let me take again the example in order to make it clear that it works. If you take the example that we had, which is a sphere, phi is equal to x squared plus y squared plus z squared minus r squared. If you take the gradient of it, you will get 2x, 2y, and 2z. This is going to be the gradient. And the vector, and then you can normalize it. The vector x, y, z is the vector which is normal to the hypersurface. So taking the gradient is always actually the normal vector to it. Now, of course, what we want is to define a unit vector. So I'm going to normalize this because this is what we want at the end. So my unit vector, normal vector and mu is going to be some epsilon d mu phi divided by the norm Okay. So there are two possible signs for n mu actually. -1 and +1 depends on which type of hypersurface actually. You have two types of hypersurfaces. There is one type of hypersurface which is called hypersurface of type space-like, and you have hypersurface of type time-like. So the thing is that if the normal vector is space-like, the hypersurface is time-like. If the normal vector is time-like, the hypersurface is space-like. What does it mean is that if you take, for example, a three-dimensional space, this is your space, and you do a foliation like that, and you consider that this is time, the normal vector is time, so it is time-like, and the surface contains only space coordinates, so it is space-like. So a hypersurface which is space-like is orthogonal to a normal vector which is time-like. Now if you define another foliation where here is an x coordinate, you know that the hypersurface contains coordinates which are t, y, and z. So we say that this hypersurface is time-like because it has a time coordinate and it is orthogonal to a space-like normal vector. So when the epsilon is -1, the hypersurface is space-like, and this one is when the epsilon is +1. Okay, so far there are mostly definitions. Another important thing is if you have a space-time, and you know what is the metric of that space-time. And now you have just a hypersurface. What is the metric induced on this hypersurface? So how to do that? So that is easy. As soon as you have your coordinate system, you just say that g mu nu dx nu, that is the metric of the full space-time, is equal to g mu nu. The dx mu is dx mu dya, the dx mu dyb, dya dyb. And this, I will identify it as the metric on my hypersurface. So this is the metric of the full space-time, and this is the metric of just the hypersurface sigma. So the metric here on the hypersurface sigma is just the derivatives of these coordinates with respect to the coordinates in the hypersurface. You can, as just a simple problem, or let me just give it as an example, if you want to see how it works for a sphere. So remember, for a sphere, we had two types of coordinates. One is the x mu, which are x, y, z, and the other one are the coordinates of the sphere, which are theta and phi. And we have a relation between them, which is r sine theta cos phi, r sine theta sine phi, and r cos theta. Okay, so imagine that you want to calculate h theta theta. H theta theta, according to our definition, is equal to g mu nu dx mu dx nu. Okay, here I'm just using the definition. Now, our space-time is just Euclidean, so this is just 1, 1, 1. It's just a diagonal metric. And you get that this is just dx d theta squared plus dy d theta squared plus dz d theta squared. If you make variation of x with respect to theta, you get an r cos theta. You square it. This one will get an r cos theta again. This will go away when you do the square, etc. And at the end, you will get r squared. And if you do the same for phi phi, you will get r squared sine theta, sine squared theta. And for the others, h theta phi, you will get 0. And this is, in fact, the metric induced on the sphere. We know that the metric induced on the sphere is this. Okay? So, very generically, every time you have a hypersurface, you want to get the metric on this hypersurface. You start with the metric of the full space-time, and then you just make derivatives with respect to the new coordinates of this hypersurface, and you get the induced metric. Okay, and so the way to see it is to say that these things here, these objects here, are like projectors. People, they write them as E nu B, which is dx nu dyb. And this is like a projector, in the sense that you have the metric in full space-time, and you multiply each index by a factor like this, and this will project the metric in all space-time into the metric in the hypersurface. So they are really like projectors. And at the end, you get the induced metric. Okay, and to finish this section, this is the last definition, the extrinsic curvature. If I'm asking you what is, if I take this, let us say that this is just the, not the cylinder, just here, the disk, and I ask if it has a curvature or not, what will be your answer? Huh? No? Why?
Because there is only one parameter theta.
Yeah.
There is no phi.
So you all agree that if I take this space-time, so this is my full space-time, just this line here, closed line, you are all saying that it doesn't have any curvature. Do you all agree with that? Yes? It's half true. There are two types. There are actually two curvatures.
Constant and constant curvature.
Yeah. There is another curvature which is related to the radius that I will talk about. The answer that you give is actually what is called the intrinsic curvature, which is what we calculate in GR, which is the curvature scalar R. This is the intrinsic curvature. It means that we don't know about, here I represent it in two dimensions. So I look to that surface in a higher space. It's just one dimension. It's a one-dimensional space, but I look at it how it is included in a two-dimensional space. And because of that, I have two curvatures. One is really what is called the intrinsic curvature. I have no knowledge of the extra dimension. It's like if I'm living here on that dimension, and I have no knowledge that there is an extra dimension or something like that, then it is flat. It is not curved. Why? Because topologically, I can always cut it and open it. It's just a line. If it is a line, it is flat. A surface of a sphere, it's not. I can cut it, open it, it will always have something. I cannot put it flat. But in one dimension, I can. So I cut it, open, it's flat. So then it has no curvature, intrinsic curvature. But it has another curvature, because we see that it does this. The other curvature is called extrinsic curvature, and usually it is written with K, and this will be the Gibbons-Hawking term, which says, how do I include a surface like this in some space-time which is bigger? And this clearly, when I include it in something bigger, I see that it has some curvature. And that curvature will be proportional to the inverse of the radius. If I take the radius much, much, much bigger, it will become much, much more flat, actually. If I take a radius very, very small, it will be much more curved. So this will be related to that. How to calculate this curvature? So it's true that in GR, or most of the time in geometry, we talk only about the intrinsic curvature. But once you want to include that Gibbons-Hawking term, you have to introduce a second type of curvature. So let me just say how to define it. Actually, it's pretty simple. We define it just with the normal vector. If you take the normal vector, nu, you see that the normal vector actually is rotating. So that means curvature, extrinsic curvature. If I have something flat, the normal vector never changes direction. So in that case, it's flat. So if it has some curvature, like something like this, then my normal vector changes direction. So if I follow this direction, I say that there is a curvature. So how do I know if there is or not? I just take the derivative of it. Of course, we are working in curved space-time, so I take a covariant derivative of the normal vector. That's it. And with that, I define the extrinsic curvature. But these indices are indices in the full space-time, so I will just project them on my hypersurface. And this will be called the extrinsic curvature. And from that, I can define a scalar K, which is just HAB, KAB. Yes?
I did not get the reason that why in the higher dimensions it will represent the curvature.
It represents the curvature in the sense of how much it is deformed in this space. So you have a two-dimensional space, which is this. I mean, that is the most natural one. That curvature is the natural one. If I ask anyone, is this curved? They will say yes. I say it is curved. So that is the curvature we say. It's just that its shape is changing. The normal vector is changing. So then I call this a curvature. If you want mathematically, it's the embedding on how I embed a hypersurface in an extra dimension. So how I include that in a more bigger space. And we always think like that. If I give a sphere, no one is thinking of the sphere in a purely mathematical way. We all think of the sphere in this way because we always include it in 3 dimensions. So I'm talking just about the surface of the sphere, but naturally I include it in 3 dimensions. Most of the time our brain includes always the hypersurface in something bigger because I see it in a natural way, in this way. So when I include that in a bigger space, I see some geometry in that big volume. But I can also just forget about that and just be an observer, just living on that hypersurface. And then I define a complete different curvature, which is R. What Einstein is doing is Einstein is saying the space-time is 4-dimensional. There is nothing more than that. So of course, this is the only curvature which has meaning. This has no meaning at all because there is no 5 dimensions.
Excuse me, sir. In that case, you have said that if we case a 2D surface, if we take a 2D surface of that cylinder, so there will be 2 curvatures. So will it be like if we open from the up, so there will be a perpendicular from the up side, and then if we open from the bottom side, then there will be a perpendicular that vector from the downside. So
No.
Is it like 2 curvatures?
No. This is the same one. Then you just follow a convention. In the sense that the normal vector, you can always define it inward or outward or inward. When you have a hypersurface, you can always define the normal vector in this direction or in this direction. You have always 2 possibilities. And this brings just a minus sign at the end. So it's just a matter of definition. So you will call it 1 over r or minus 1 over r. In the literature, you will find both actual conventions. In fact, in mathematics, they are using a convention which is not the one we use in physics. But it's just a minus sign between them. But there is no 2 different extrinsic curvatures. It's only one related by a minus sign.
Okay. Can you say something more about this definition actually?
Definition, yeah, that's right.
This definition here.
How it is different means if normal curvature is okay.
Yes.
That is our scalar curvature which we are knowing from GIAN. But how do you define intrinsic curvature? Means in a formula and also in a practical manner.
Intrinsic is this one. This one is the extrinsic one. So the extrinsic one actually is the one which has been introduced historically first. It might have been introduced by Gauss actually. So that is the natural thing actually. Einstein just actually washed our brain in some way, and we are all now have habit of this one. But as I was saying, if, let me take an example, I don't know, if I take a cylinder. If I take a cylinder and I ask someone who never studied geometry if it has curvature or not, he will say, yes, of course. It is like that. It has curvature. Why? Because I see that the normal vector is actually, mathematically, is rotating. It's changing direction. So the curve, that space is curved. But it's just because I include it in a bigger space. That's just that. But if I am someone living on that hypersurface, I have no knowledge of this. If I have this, or if I open it with identification of these two lines, this is for me exactly the same geometry. Nothing has changed between them, if I open it or not. And this is flat, so this one is also flat. From a local point of view, for the other curvature.
That's the matter of taking that primitive dimension. We are going to the higher dimension and then seeing it.
Yes, exactly.
So then why we are using these projection operators rather than this G mu?
No, because G mu is not a projector. The reason is because we want to define at the end an object which is related just, we are going to work with only the hypersurface at the end. So we want to define really an object which is defined.
Normal vector is fine, and when we are doing its covariant derivative,
Yes.
so it is
Actually, it's the same.
divergence of the normal vector.
Divergence, yes.
Divergence of normal vector, and then we are multiplying it with the projection operators, then we
Yes.
are projecting it to some surface.
Yes.
Surfaces.
Yes.
So how will it make that
Make what?
that K?
Not sure to get the question. How it will make K? What do you mean?
I'm just saying that we are just taking the divergence of the normal vector.
Yes.
And then multiplying with the projection
Yes.
vectors.
Yes.
And then we are going where?
Yes.
Going where we are.
Actually, how this definition makes sense, something related to curvature actually. That's
No. Yeah, forget about projection. If, okay, I'm not sure about this question, but if I answer this question, curvature is this, if you want. As I was saying before, it's the most natural definition. Imagine you have a hypersurface which is flat. The normal vector points always in the same direction. If you take the derivative of the normal vector, it will be 0. So this will have no curvature. If I have a hypersurface like this, my normal vector changes direction. If I take the derivative of it, it will not be 0. Yeah? That's why we take derivative. Derivative will tell me if the normal vector is changing or not. If it changes, then there is curvature. If it doesn't change, it is just going to be shifted like that. There is no curvature. Yeah?
So means here your that EMU, EBMU, these are the bases, no? This is the base, no? And you are taking projection on it.
Yes, yes, yes. So yeah, at the end I want to have an object which is defined because the normal vector goes away from the hypersurface. When I take the covariant derivative, I still have an object which is defined in full space. So yes, so I project it to have a tensor KB, which is defined just on that hypersurface actually.
So what you intend to tell is that the curvature which is normally defined,
Yeah.
that we define, we take normal to this on the surface or on the surface of it, and then we take a derivative, and then we take a projection on the projection on the basis of this. So, and then you will get some the definition that is the curvature in the lower dimension.
Yes.
That is the point, no?
Exactly.
Yeah.
Yes.
And that is known as intrinsic curvature.
Exactly.
Sorry.
Extrinsic. So you can, if you know the book by Poisson, a toolkit, huh? Yeah, no, not relative. Yeah, maybe, yes, maybe, yes. Exactly, yes. So if you look, okay. So if you take that book, actually you will find all the details about that because he goes to the black hole physics, and for black holes it's quite important to define that. And if you want to define all the Hamiltonian formalism of GR, you have to go to that, okay? So in this book you will find much more details about it. Okay, so let me try to move a bit more. Okay, so then you have the full calculation in GR, which is a bit long, but I put it completely because somehow you will not find it in any book. I don't know why. They just put it without the calculation. So let me just summarize what is happening is that in general relativity, if you take our favorite action, which is defined like this, and you make a variation of it, you get actually one term is the easy part to get. You get this. But then you get an extra term which actually you can write you can write like as the divergence of a vector, and this vector is going to be G mu beta, G alpha gamma minus G mu alpha, G beta gamma, covariant derivative of beta gamma. So actually this term is going to be a surface term, and we will have difficulties actually to cancel it because of what I was talking about before. If you use Dirichlet boundary condition or Neumann boundary condition, you will not be able to remove it. So you have all the calculations with details in the notes, and at the end what we get is that actually you need to add a term which is plus 2. The integral in 3 dimensions, H is the induced metric in 3 dimensions, and this. This is the action of general relativity. It's not only the first term, plus matter if you want to add some matter, etc. Of course. But this will be the full thing. You have GR plus a boundary term in 3 dimensions with a metric H which is induced and the extrinsic curvature. If you have this term is called the Gibbons-Hawking term. Then now you can make the variation, do the full calculation, and you'll find that GR is now well defined. So okay, so this is the standard thing in GR, and for us, we are going to do something a bit similar. In the sense that now I'm going to talk about extra dimensions. So when we work in extra dimensions, there are, up to now we have never observed these extra dimensions. So we have to think in a way why we don't observe them. So there are actually 2 different schools which have 2 different logics if we have extra dimensions. One is thinking of extra dimension, large extra dimensions. And the other one is compactified extra dimension. So you have these two possibilities. The first one, we talked about it last time, is to say that there are some extra dimensions, but these extra dimensions actually are compactified. So this will be, for example, an extra dimension. So in the sense that you say that actually we have extra dimensions, how many we want depends on the theory, but that extra dimension will be extremely small and actually compactified, so it has some periodicity. So this is the theories like, for example, string theory. They don't consider one, but 6 extra dimensions, and they are compactified in a very specific way, in specific geometry. Okay, so this is one possibility, and to say that I don't observe it because I don't have enough energy to look at it. So you say that, okay, this is our space-time. This dimension, we see it very well, fine. The extra dimension, if I put it very, very far, you will not see this extra dimension. You will think that it is just a line. If I see this from very long distance, I will just see that. I will not see the extra dimension. So I will say that it has only one extra dimension. But if I make a zoom, means that if I go to higher energies, I will start looking to this extra dimension. But it will be at the scale of Planck, and so far we don't have at all the possibility to go to these energies. So this is a way to think of extra dimension and at the same time being compatible with all observations because we don't observe them. So they exist, but they are compactified and very small. That is the first possibility. The second possibility, which are, now this is the second, the compactified one. The first one is called large extra dimension. So now the extra dimension is large. This is my space, 4-dimensional space, but I have an extra dimension which exists. I will call it W, for example. So this extra dimension exists, and it is a large extra dimension. It's not at all compactified. So how is it possible that we have never observed it? The reason is that we are stuck on this hypersurface. We cannot move from it, actually. Okay? So because of that, we cannot go on these extra dimensions. We would need much more energies to be able to escape in some way from this extra dimension and see the additional dimension. So in this case, it is fine enough also to have an extra dimension like that. This is like string theory. This is the best example of this kind of theories, and these are called brand models, which are also related to string theory. At the end of the day, most of the things are related to string theory. At least the idea comes from string theory. Question so far?
Professor,
Yeah.
if you make a torus from the cylinder, then how many dimensions does it have?
It has, if you are talking only the surface, is 2. It's 2 dimensions. If you consider also the radius as a dimension, is 3. But otherwise, it's 2 dimensions.
So I have a question with this action. That means you are adding the extrinsic curvature term, no?
Yes.
That action.
Yes.
Einstein action.
Yes, to eliminate, because when I do the variation of that, I'm getting like for the toy model that I used before for L equal to Q double dot, I'm getting a delta Q and delta Q dot. When I was doing this Lagrangian, and I made the variation of it, I'm getting a boundary term with delta Q and delta Q dot that I had to fix on T1 and T2, and I couldn't kill them at the same time. So what we did was to add a boundary term, which was this one. And then we killed one of them. Here it's the same. We have something on the boundary which is going to come with the metric and the derivative of the metric. So we add this term, which is going to kill the derivatives of the metric. And now we will end with just something where there is delta G mu. And delta G mu, we can fix it to be 0 on the hypersurface, actually. So then we have a well-posed problem, actually. The thing is that I cannot impose too many conditions. I have just a second-order differential equation, and it will not make sense to fix 4 conditions, for example. I can impose only 2.
Sir,
Yes?
so do we take the time as large extra dimension or not?
No, they are usually it's space. So usually this coordinate is space. There are a few people. So here we have t, x, y, z. So we have already a time here, and the extra dimension is space. Mostly everyone does this. I've seen just few people, and mostly there was someone in Ayuka who did this, Varun Sani, who at some point of time, he looked also to possibilities of having a time coordinate here. But then you have 2 time coordinates. What's the problem with 2 time coordinates? Is that if I have 2 space coordinates, for example, x and y, I can have a motion like that without any problem. This is not a problem at all. I just move like this and come back to the same point. If I have 2 time coordinates, there is no problem to do that also. I should be able to make a loop because I have 2 time coordinates. So, but that means that I can go and come back, etc. So I will influence myself. So I will produce actually causal problems because I'm producing loops like that in time. So if you add a time coordinate, you will have actually causality problems.
If it is there, so there can be many universes embedded like that within this bigger.
Mm-hmm. There are theories for that, yes. There are plenty of things like that. But for example, if you consider something which is called the first model was introduced by Randall and Sundrum in 1999. And what they did 2 models. One with 2 branes, actually. You have one universe, and you have a second universe. And they are connected by some extra dimension. So we are living somewhere here, but there is a second universe that they call the anti-universe or something like that. And then after that, they move to only the possibility of one brane, one universe. It is much simpler. But you can imagine many more hypersurfaces. It's perfectly fine, producing some additional particles if you have extra dimensions. So you should observe something. So far, nothing has been observed. It doesn't mean that it doesn't work, because most of these theories are at very high energies. So at our energies, we should not observe anything, actually. One thing that I wanted to say on these extra dimensions, and I forgot it.
This is expected to be, this extra dimension is expected to be emerged at very high energies, no?
Yes,
That
exactly.
means near singularities and all. Means black hole singularity, means in black hole there is singularity, we say, no? So near that it's supposed to be, because at that the rho will be very high, no? Density would be very very high. And
Yeah, I would not say density large for black hole singularity because the solution is defined in the vacuum, and I will not be able to define quantities like density, etc. But at high energy, yes. So whatever the physics at high energy, if it is a black hole, then it's fine. It should have at least some consequences on how the structure of the black hole is, etc.
and
But
then means the curvature will go to infinity, scalar curvature.
where? No. Okay, for example,
Near singularity.
not necessarily. For Schwarzschild solution, the curvature scalar is 0 everywhere. What is?
I'm talking about black hole. Black hole.
Yes. Yeah, if you take a black hole, the curvature scalar R is 0 at the singularity also. What is diverging is another scalar which is called the Kretschmann scalar. But the curvature scalar R is 0 everywhere, actually. So curvature, the thing is the following, is that curvature is a complicated thing. We cannot represent it with only one scalar. So you have to, it's the metric, the full knowledge. So this is why if you want to talk about scalars, you have to consider all type of scalars. All these are scalars. This one is 0, this one is 0, this one is not 0, and it will diverge. And this one will diverge. But with only one scalar, you cannot represent everything because it has much more complicated structure. One of the motivation of these extra dimensions actually was this again, cosmological constant problem, in the sense to say that we have we have here some matter, so we have matter fields, and they produce this vacuum energy. But that vacuum energy, which is huge, actually produces effects principally in the extra dimension. So in some sense, we get some form of dilution of this vacuum energy. So this vacuum energy curves the full space-time and not only our brain. So there is a huge vacuum energy, but it gets diluted in the extra dimension. So because of that, we don't see it much here. So that was one of the motivation. The other things are more in terms of structures. There are some theories which demands extra dimension. String theory, for example. When you want to write it in a consistent way and not have some problems, some tachyonic, some ghost, etc., you have to work in extra dimension. If you take supersymmetry, almost exactly supergravity, which is an extension of, supposedly an extension of GR, and you want to write it in a consistent way without having any trouble, you need also extra dimension. So there are motivations also from a mathematical point of view. So at some point of time, you are guided only by mathematics. You say that I want to define a theory which is consistent mathematically. Then at the end, if it produces something nice, physically, maybe or not, but at least mathematically, I want it to be sure, to be well-defined, that it has everything, the Cauchy problem well-defined, it doesn't have ghosts, it doesn't have things which are going faster than speed of light, etc. So as soon as you define everything like that, some theories demand extra dimensions. So then we are forced to work with them. And then from a phenomenological point of view, you can say, what is the implication of that? And that is what we are going to see after, is that this, if you believe that there is an extra dimension, I have an action now which is going to be in 5 dimensions. I will have something like that, but actually I can reduce that to an action in 4 dimensions with a scalar field. So the scalar field will have, in some sense, it's like what we did yesterday. We found some equivalence. So this will be equivalent to an action in 4 dimensions where I have GR plus some scalar field. So they will be in some sense equivalent. And that scalar field, I'm going to call it Galilean. And that scalar field actually tells us more or less the position of the brain. If I have a brain which is like that, my hypersurface, this position, I will call it phi of x. It changes here. So here the position is larger than here, etc. So it changes with the position x. So it is like a scalar field. So it tells me about the position of that hypersurface in extra dimensions, and we call it Galilean. And with that, you get some action here, and you can start working its phenomenology, cosmology, black hole physics, and everything else. I don't know if you have questions.
But it means that we are imagining the extra dimension because there are some of the events which we cannot understand. So that is the main reason. No, like high energy, there may be some
No,
events.
yeah. This is in some sense a practical reason to say I have a problem, which is an observational problem. I observe acceleration, etc. I cannot explain it, so I will consider this thing. But there is another way, which is just a mathematical structure, is to say that some theories which do have some beauty, like supersymmetry and supergravity, because they have some nice symmetries, etc., I want them to be consistent. They demand extra dimension. String theory demands extra dimension.
Yeah.
So there are some theories without thinking about observations, just the mathematical structure is if I wanted to write it correctly, I need to live with extra dimensions. And that is actually, in history of physics, it's really a big change because up to now, up to the 19th century, we have always thought dimensions as just a parameter. I fix it by hand. I say we are in 3 dimensions, or after Einstein, we are in 4 dimensions, but I put it by hand. Now, it's not like that. The theories are telling us how many dimensions it is, only just to be consistent. String theory is what it does. It doesn't allow us to do whatever we want. It says if you want string theory, you need to work in 10 dimensions. You don't have choice. So in some sense, we lose that freedom, which is very good, because choosing by ourselves the number of dimensions is a bit arbitrary. Why 4? Maybe there are 5 or 6 or 7. So the theory is imposing that. But then after that, of course, it has to be consistent with everything. And so far, we are pretty far from that.
Can you repeat this argument of Randall Sundaram?
There are 2 models, actually.
And the weakness.
The what?
Weakness of the arguments. Is there any fault in the arguments or?
No.
Okay.
No, it's...
What is the? Can you repeat the arguments again?
Which one?
Randall Sundaram.
The arguments, or you mean the model, what it is?
Uh-huh.
Yeah. So the model is, they propose 2 actual models based from string theory. To say that one is that you have 2 brains. One is our universe, the other one is some anti-universe, and connected by some extra dimension. And we are living just here. And here maybe there is some other people living. And then they understood that actually you don't have to consider this. It's much simpler just to do something else, which is to consider only one space, but the extra dimension is ADS. So actually, in some sense, the gravity will just become weaker at some distance. So it has a geometry, if you want, which has something like that. So we have difficulties to escape just because the bulk is a bulk which is ADS. And again, that is quite a popular thing to consider something which is ADS. The very interesting thing about ADS is the following, is that imagine that you have a cosmological constant which comes from the brain that I will call lambda, which is our vacuum energy. And let's suppose that here in the bulk I have also a lambda which is negative because it's ADS. Now actually, when we are here living on this brain, we are not measuring only this lambda, but we are measuring actually some kind of effect of both of them. So we measure some lambda effective, which is this lambda here, lambda squared, I think it is, plus the other lambda. So if this lambda is negative, you see that it can cancel out a bit the vacuum energy. So you have some vacuum energy here, which is negative because of the geometry, which is because of ADS. You have vacuum energy here produced by the matter. And when you make the summation of both of them, you can get maybe 0. But of course, there is fine-tuning. You have to choose this parameter exactly to cancel it. So it doesn't solve the cosmological constant problem, but it's an interesting idea to say that the extra dimension, this energy there, will contribute actually to what we see here. So that's one of the motivations also. Okay, so let me try to go to what is called Galilean and to try to show a bit the Einstein mechanism. Unfortunately, we don't have much time today, so I will just cut it a bit, and then you will have more details in the notes. So the idea that I was explaining this morning is that imagine that we have 5D, and I make what is called a foliation of this 5-dimensional space-time. So I have 5-dimensional space-time, and these are just the space-time that I make a foliation of it. And I will consider some direction like this. And this position here, I will say, that, I can even take this value here. I will consider this coordinate to be 0 here. This coordinate, I call it phi, actually. So I have phi equal to 0. This is phi equal to 1, phi equal to 2, 3, 4, etc. This is my foliation. Now what's happening is that imagine that we have a brain in this space-time. So it has some structure like this. So this is my hypersurface, which is in this 5-dimensional space. So you have to imagine that this has 4 dimensions, actually. So what is happening is that it bends, it has a curvature in this space-time, and if you want to measure what is the position compared to a position of equilibrium, you have this deviation here. This deviation depends on the position x. This is the coordinates x. So you have some phi of x here. Here you have another position. Here the position is negative, etc. So the position of the brain it's called a brain. We are going to say it's phi of x. This is going just to tell me about the position of it. Okay? So actually we are going to get an effective theory with this phi in our action, and we consider it as a scalar field. But what is the origin of the scalar field is the position of the brain. So in many theories that you will see in cosmology, in gravity, when people they take a black hole or to explain dark energy, they add a scalar field. Now, the origin of the scalar field can be really, really large. One origin is this. It's just the position of the brain. Another origin, this morning I was talking about compactified dimension. If you compactify the dimension and you have here the radius of this compactified dimension, that radius might depend on time and also on the position. So it becomes a scalar field. So this is another one, which is going to be called the dilaton. We have seen last time a theory like f of r. F of r is also r plus a scalar field, which is called, in this case, the scalaron. The scalaron, sorry. So actually, this is a scalaron, this is the dilaton. You have, and this one is the Galilean. So you have different names, different origin, etc. But at the end of the day, what you have very often is just some scalar field. So what is the origin of the scalar field? That might be very difficult to say. But from if you want to be just phenomenologist, you can say, I don't care about its origin. I have a scalar field, and then I work with it, and I try to see how much can I test if this scalar field exists or not. Can I observe it? Can I measure it? Can I detect it? So then comes all the phenomenology about it, etc. So let's continue a bit about this Galilean. So how to get really an action from that? There are different ways. I'm just giving the simplest one, of course, because it's the simplest way. It's not completely rigorous, but it's fine enough actually to understand what does it mean. So let me say that we have some coordinates in 5 dimensions that I will call x mu. And the coordinates of the brain, I will call them x small mu. So these coordinates are going to be t, x, y, z, and phi, for example. These are the coordinates here, and this one has coordinate t, x, y, and z. So these are the coordinates of what is called the bulk, and this one is the coordinate of what is called the brain. Okay, so now we have done this morning we have seen how to calculate the extrinsic curvature of some hypersurface like that. So first of all, I need to define the position and then the equation of motion. The equation is that the x mu is going to be x mu, and the x5 is going to be the phi x. This is the equation of my brain in the sense that it has some coordinates here, t, x, y, z, which are exactly the same. So x mu is just x mu. But the extra coordinate phi is a function of the other coordinates x mu. So this is the equation of my brain. And now I will consider that there is 2 metrics, one of the full space-time, and there is a metric of just the brain here, which I will call, like this morning, HAB, and this is G mu nu, the metric of the full space-time. So just for simplicity, I will consider that 5-dimensional space-time is Minkowski. Of course, you can take it as you want, but just for simplicity, I will say that the full space-time is Minkowski. So we are just trying to include a hypersurface in a Minkowski space-time. That will make it simple, and it's just to understand how it comes. So the G mu nu is actually just the metric of Minkowski space-time. Now, what is H? H, the induced metric, as we saw this morning, the formula, you have that HAB is just the variation of these coordinates compared to these ones, which are the projectors, and G mu nu. So you just take the metric in 5 dimensions and you just project each index with this projector that we saw this morning, except that this morning we called it Y, but it's the same thing. Okay, so we have this. The derivative is pretty simple. When the index here goes like t, x, y, z, these 2 coordinates are the same. So it will not give anything, it will just give 1 actually. So it will be just the G mu nu there. But when we have x5 is equal to 5, when mu and nu are equal to 5, you have phi actually. So then you get actually the derivative. You get plus dA phi dB phi. So this is my induced metric. So you see that we started with a space which was flat, G mu is flat, but now the subspace, which is just this brane here, has a curvature. At least the metric is not flat, it has this. Of course, if phi is 0, is a constant, means that the brane is just like this, for example, then phi does not depend on the position, then the derivative is 0, we induce a metric which is also Minkowski. So the induced metric depends on the position of the brane. Yes?
So coordinate must be mutually independent, but how will you justify the x5?
No, they are not independent. The coordinates are independent, but the equation is a constraint on the coordinates. What we saw this morning, for example, if you take a sphere, the coordinates x, y, z are independent, but the equation is a constraint on the coordinates. It's a restriction of the coordinates. So an equation of a surface will be always a constraint on these coordinates. So here it's the same. We are saying that the coordinate x5 is a function of these other things. Like, for example, I don't know, you have a hypersurface, or you have something like this. This is z, this is x, so you call that z is some function of x. That will be the equation of our. So here my coordinate is phi. So phi is the x phi is phi actually. It is a function of the other coordinates x.
So phi is not a unique function.
It's not
A unique function. Could be anything in the, let's say, in a two-dimensional space. That is f of x.
yeah, I didn't define yet phi for sure. Yes. And at the same time, but here, just for this particular case, because this full space-time is Minkowski, I have some symmetry. If I want not to call this phi equal to 0, but to call this phi equal to 0, nothing will change in the physics. So in that sense, I can shift that the position of that hypersurface anywhere, and I will not change at all the physics. So my theory should be invariant and translation. And this is what we see here. If to phi I add a constant, it doesn't change anything. Everything comes with a derivative. So, and at the same time, I can make a rotation. If I make a rotation of this hypersurface, nothing will change because the full space-time is flat. It's Minkowski. So this Galilean field will have a symmetry, which is why it's called Galilean. It's because it has a Galilean symmetry by translation and by rotation. That symmetry comes only because this hypersurface, you can change it, the position, you can translate it and you can rotate it without changing anything because the full space-time is Minkowski. So there is no privileged direction. So then it has this symmetry, and because of that, they call it Galilean, actually. This is the original reason for that. Okay, so if we have this, and we have the equation of our brane, we can also get the equation of the normal vector. We want to know what is the normal vector here to this brane. So the normal vector, as we said, is just the derivative of this this equation. So it will be like 1, 1, and some d mu of phi. Yes.
So we are specifying position of the brain and the equation of the brain with the same phi of x.
The position of the brain and
We have written a position
Yes.
of the brain and phi of x.
yes,
And that phi of x mu is equation of
it's the position of the brain. So let me say it differently, maybe.
these two things are different.
Which two things?
Position of the brain and equation of brain. Equation of the hyperspace of the brain.
The hypersurface is the brain. The position of the brain is its equation.
Okay, its equation is
Yes.
the position of the
Yes. Yes. So just to be sure for everyone, if I take in 3 dimensions some x, y, and z, the equation here of my surface, I can write it as z as a function of the other coordinates. Z as a function of x and y, and this will give me the equation of my brain. So here it's the same. The additional direction, I call it phi, and it will be a phi of x means t, x, y, z. Okay, so sorry for the brain, the normal vector. The normal vector is when you have an equation which is this equation. This is the equation of our brain. When you have an equation of this form, which is like a parametric equation, in order to get the normal vector, you take the differential of that. You get dx phi minus the d mu phi dx mu equal to 0. The coefficient which appear in front, they define the normal vector. So the normal vector will have a coefficient d mu phi and minus 1. That will be your normal vector, actually. So you see again that if phi is constant, if we have just a plane like this here, the derivative is 0, the normal vector will be just minus 1, it will be just this vector. But if you start having some variation of phi, the normal vector changes. So this normal vector now you can normalize it. I will not do that. So you normalize it, it's easy. And from that you can calculate the extrinsic curvature, which is just the derivative of that. You will have the notes here, and at the end you get K, the extrinsic curvature. So getting the extrinsic curvature now, it's this. You get this formula. You get that K is equal to minus box phi divided by 1 plus d phi squared plus d mu phi d mu nu phi d nu phi divided by 1 plus d phi squared 3/2. Okay. So this is the extrinsic curvature that you would calculate. If you do everything, you have the normal vector, you normalize it, you take the derivative of it, you project that, and you get the extrinsic curvature. Okay, so that is the extrinsic curvature, but why are we doing all that? In order to reduce our action. What is the action originally? Originally, the action, we are working in 5 dimensions. So in 5 dimensions, the action will be something like that. We just go with the theory of Einstein. We have R, and now we add actually the Gibbons-Hawking term in order to define well our problem. This is why I was talking about that this morning. Of course, I could have also some cosmological constant in 4 dimensions, that is perfectly fine. So this is going to be our action. This is more or less what is called the Randall-Sundrum model. So I'm doing exactly general relativity, but instead of doing it in 4D, I do it in 5D. So this is GR, put in 5D. There is the boundary term, which is supposed to be always there, but except that now boundary is in 4 dimensions, so it will be very interesting for us, plus a cosmological constant. So that will be my action. Remember that our bulk, the full space-time, is flat. So the curvature scalar is 0 in this case. So actually this is why it simplifies a lot my action. So my action is just this and this actually. K, I have it already. This is this term. I just have to calculate the square root of minus h, and that's it. So let me just, this is just a small mathematical thing for the ones who never did this kind of calculations of the determinant of a metric. We have an h mu, which is equal to eta mu plus d mu phi d nu phi. How do I calculate the determinant of something like that? There, for that, we use a formula which says that the determinant of a matrix is equal to the exponential of the trace of the log of that same matrix. I don't know if you all know this formula. You should know it when you derive the equation of general relativity. You have the square root of minus g in the action, and you want to make a variation of that. If you want to make a variation of this, you have to know this thing. You can check it very easily. Imagine that you take a matrix which is diagonal. Okay, for example, imagine you take a matrix which is just diagonal. The log of this will be log 1, log lambda 1, log lambda n, and minus infinity here. And you take the trace. So the trace will be just log lambda 1 plus log lambda 2 plus etc. The exponential of each one will give lambda 1 times lambda 2 times lambda n, which is exactly the determinant. So it works for a diagonal matrix. Now, because we are working with a symmetric matrix, and we know that a symmetric matrix can always be diagonalized, so you diagonalize that matrix, you get some matrix which can be written like P, D, P minus 1. This is diagonal. This is just a matrix to go from one to the other, and you can conclude. So that is true for any matrix which is symmetric. We can always write it in this way. Okay, so what do we have here? We have to calculate the log of eta mu nu plus d mu phi d nu phi. I put this calculation because these kind of things can happen very often in many situations. So better to know how to do it at least once. So let me factorize the log of eta. Plus, I will write it like this, like the matrix identity. Okay, so what I did is just, I factorized the matrix here, eta mu nu. So I got then 1 plus 1 index here up, 1 index down, and the product of these two, the log goes like the summation, so I'm getting this. So now what I'm going to do here is to make a series expansion. Log of 1 plus x is x plus or minus x squared divided by 2. So I take this square, so I get d mu phi d nu phi times d nu phi d, this one I should call it alpha, d nu phi divided by 2, etc., etc. I should maybe write here, otherwise it's not clear. Okay, so you have its log of eta mu plus what you have is d mu phi d nu phi plus or minus d mu phi. There is a kinetic term that we got, d nu phi divided by 2, etc. And you take the trace of that. Means you are just going to take that mu is equal to nu. So taking the trace, this one I just keep it like that, trace of log eta mu nu. This one gives d phi squared minus, here I'm getting another d phi squared, so it becomes d phi 4 over 2 plus d phi 6 over 3, etc. And then I take the exponential of this. So this will just give me the determinant of eta mu nu. And the exponential, and this is the log of 1 plus d phi squared. So it gives, so we killed completely the indices. And for that, we have now that minus square root of h is equal, this is just minus 1 plus d phi squared, square root of it. Okay, so with this, we have everything. So now we can write our action, this action here, square root of minus h, we have it, k, we have it, lambda, we have it. So we have our effective action. I just have to replace that. So our action becomes, there was a minus 2 d4x. The square root of minus h is just this times this. I'm getting a minus box phi, and I'm getting a complicated term here. Okay, that is one term. And then there was also the minus 2 lambda. So lambda 1 plus d phi squared. Okay, so that is my action. So now we have an action with a scalar field which comes from this extra dimension. We don't have gravity because I killed it from the beginning. I consider that the bulk was Minkowski. If I don't want to kill it, I have to consider that the bulk has some gravity so that it has some metric. So you can do it, play the game with a bulk which has any metric g mu, and you will get something here which has also gravity. But here I can just keep it like that. That's simple. This is a total derivative. It goes away. This I can reorder a bit things. You will find the details in the notes. And at the end, I will get an action which is the following. This is just going to be the integral of d4x box phi log 1 plus d phi squared and minus 2 lambda 1 plus d phi squared. So this is our final action, just by doing some integration by parts here. In the limit where d phi squared is small, what does it mean? it means that our brain is vibrating, but not too fast. So the kinetic term, it remains small, actually. So we have something which is not relativistic. If I do this approximation, the log of 1 plus this is just this. So I'm getting something which is just this term. And here I'm just getting a kinetic term, actually. So you see now, what do we get? We get an action which is with a scalar field, which has a kinetic term, as any kind of scalar field, but it has a very nonlinear term here. It's not like quintessence. Quintessence, you have this plus a potential. Here we don't have a potential, we have derivatives, okay? So that is what we call the Galilean action, actually. Make some small break if you have questions. Or you got lost in the process. Okay, so in this case, let me continue and show just from a phenomenological point of view what's happening. Let's suppose that you don't want to know from where it comes from. And you just start with this action, and you want to know what's happening with it. So I will look at it. This is the Galilean. There was a lot of literature on that. It has some very interesting features and some also negative ones. And it has a mechanism for this scalar field to hide, actually. So my scalar field that I had before, let me just, maybe I should rewrite it, actually. And we have, I will write it now like this, minus 1/2. So I just normalize a bit things. There was some constant d phi squared, box phi. That was my action. Okay. So what can we do with that? We can actually make a variation of this action and get the equation of motion. Okay, so let me do this. I make a variation of this. I'm getting this integral here. Here I'm getting minus d mu phi, d mu delta phi. We have here a plus 2 alpha d mu phi, d mu delta phi box phi plus alpha d phi squared box delta phi. Okay, so I'm doing the integration by part, and I'm getting then here it becomes a plus box phi delta phi. This one, there is a d mu here, so it becomes a minus 2 alpha, and there is a derivative on d mu phi box phi delta phi. And this one, we have to do two integration by parts, so it's plus alpha box of d phi squared delta phi. So my equation of motion is the following, is box phi minus 2 alpha box phi squared, when I do this, minus 2 alpha is d mu phi d mu box phi, and then I have the last term here, which is box d phi squared equal to 0. So this is our equation of motion. This one I can expand it a bit because it will simplify things. It's a double derivative. The first derivative will give me 2 d mu nu phi d nu phi, and then the second one will give us twice the box d nu phi, d nu phi, and plus 2 d mu nu phi, d mu nu phi. This one should cancel with this one. So what we have at the end is this equation, box phi minus 2 alpha box phi squared minus d mu nu phi d mu nu phi equal to 0. Okay, so this is the equation of motion. So even if I start with a theory which has a lot of derivatives, this one has 2 derivatives. There is a derivative over phi, but it's squared, so it has 2 derivatives. Here we have 2 derivatives, 2 derivatives. We have 4 derivatives. Usually when we have so many derivatives, we expect to have an equation of motion which is super complicated. But the equation of motion at the end is second order. It's a second order differential equation. There are no third derivative. Second derivative squared, but it is a second derivative. So the very interesting thing about these theories is that even if they have very high number of derivatives in the action, at the end, you can even add much more, actually. People, they started generalizing this and having much more complicated theories, like something called Ondensky. But at the end of the day, you have an equation of motion which is just second order. Yes. Yes. This is why we get plus. Yes. So the very interesting thing is that it has a second order differential equation. I didn't talk about this lecture about this Ostrogradsky ghost, but this is really a very fundamental thing that we would like to keep, to always have a second order differential equation in order not to have troubles later on how well defined is the theory. Okay, so this will be the equation of motion. Now what can we do with it? When you do, as I said, what the derivation I did, that starting from 5 dimension, reducing it to 4 dimension, I made it in a simple way, in some sense, but actually if you do it more in a more serious way, what you get is a coupling to matter. So here we have a coupling actually to matter. So matter is coupled to this scalar field. So then we can be in trouble actually, because if matter is coupled to the scalar field, as we saw, the scalar field start pushing matter out from geodesics, and that is the 5th force, and we have never measured that. So we have an extra degree of freedom, which is the scalar field, and we have never observed it. So the main question is how to make these theories viable. For this, we have to kill it in some way. So again, there is a mechanism, a screening mechanism, and that screening mechanism is called Einstein. We don't put it by hand, it's there actually. We just have to look at it to see clearly if it is there or not. So I will do a simple thing to show it. I'm going to study a spherically symmetric solution, but flat. We are in flat space-time, but let us look to a spherically symmetric solution. Okay, in a spherically symmetric solution, box phi is just phi double prime plus 2 divided by r phi prime. This is just the D'Alembertian. This, you have it. This one will be more or less just the phi double prime squared. So you can calculate this, and you get the equation for a spherically symmetric case. This, by the way, you can write it in this way. It's 1 over r squared.
Sir, phi is the function of r or x?
Yeah, sorry. Because I say it's spherically symmetric, so I'm saying here that phi is just a function of r. Yes? And I should say static also. Static, spherically symmetric. Okay, so then I'm looking to a function like this, and I'm having, this is really just r squared phi prime actually. And from that we can get the equation of motion, and the equation of motion becomes 1 over r squared, this term here, r squared phi prime plus 2 alpha over r squared, again d dr of r phi prime squared equal to minus beta t. So which means that if I multiply everything by t squared, I can integrate it, and I have that r squared phi prime plus 2 alpha r phi prime squared is equal to minus beta, the integral of t times r squared dr. Taking only dust, if you take some planet or something like that, this is what we are studying, a spherically symmetric solution around something with a small gravitational field, like a planet, for example. So then the energy momentum tensor is just minus the density. So this is equal to beta, the integral of density r squared dr, which is called just the mass of the object. Questions so far? So this is just the mass of your object that you are studying now. So I'm not talking about a black hole, but any massive object that you might study. So you have that r squared phi prime plus 2 alpha r phi prime squared is equal to beta m. So let's look to different situations. First of all, let me see if I didn't have these nonlinear terms. So I kill all the nonlinear term. I keep only that kinetic term. Then the solution is trivial, that phi prime is equal to beta m over r squared. But if you remember what we did yesterday, we said that the fifth force divided by the mass is equal to beta, the gradient of the scalar field, which means for us beta phi prime. The force is proportional just to the gradient. So this is the force produced by that scalar field. And that force goes like 1 over r squared, exactly like Newton. So we have a force which is, if beta is of the order 1, we have a force which is exactly of the same amplitude, the same order than the Newtonian force. And we have never observed it. So that's, of course, impossible. So this is why, if alpha is equal to 0, we run into troubles. Now, if alpha is different from 0, you have this second-order algebraic equation. You have two solutions. One solution will be better than the other. So I will take that solution, and it's the one with a minus sign. R over 4 alpha minus 1 plus 1 plus 8 alpha beta m divided by R3, square root of this. Okay. So that is our force, actually. I mean, proportional to the force, because we know that phi prime is proportional to the force. So what's happening? At large scales, so means when R is very, very large. If R is very large, this is 1 plus 4 alpha beta m over R3. These two terms, they cancel each other. We have 1 over R3. With this R, it gives 1 over R squared. Phi prime is of the order beta m over R squared. So we have a force which is like Newton. Now if we are at small scales, so when R is very, very small, then this term is dominant. So I have R 3/2. With this, it gives 1 over square root. 1 over square root of R. And this is extremely negligible compared to the Newtonian force at small distances. So this mechanism, what it says, is the following, if I want to summarize it. Imagine I consider a spherical object, like the Earth, for example. So I have a spherical object here. Now what's happening is that if I am at very, very, very small distances, so if I'm on some radius here, all here around, the fifth force is very, very negligible compared to the Newtonian force. I will never observe it, and this is what we see here. Up to some scale, which is called the Weinstein radius. After that, my fifth force is of the same order than the Newtonian force. So if I go at very, very large scales, I'm getting an additional force which can produce, for example, the acceleration of the universe. But at small scales, that force is completely suppressed compared to the other one. And why? Just because of the alpha. And the alpha comes from the nonlinear terms, that box phi times g phi squared. To explain it in a different way, let me say it's just an explanation by hand in some sense. Let me go back to the action. The action says the following. The action. This is the, if you want, the most important part to understand about this mechanism. And you can have a coupling to matter, like this. Now the following is happening. When these nonlinear terms, they start becoming very dominant, we just suppress completely the additional force. Why do we have this? I can rewrite this as minus half 1 minus 2 alpha box phi, g phi squared. Up to now is okay. It's just rewriting a bit things. Now, this term is going to be minus 1/2 z. I just redefine it as a z. And then there is the other term, b phi t. Okay. So what I can do is that, let us suppose that I can do it, that I redefine, because I want a canonical scalar field, I redefine this in this way in order to absorb this z here. So then this Lagrangian becomes minus 1/2 d psi squared. I have a canonical scalar field, or kinetic term, plus beta, and the phi becomes psi divided by z t. These two here are equivalent. But now I have a canonical scalar field. So I understand it in a better way. What can I say now? When this term becomes large, when the nonlinear term becomes very, very large, Z becomes large. If Z becomes large, the coupling to matter will disappear. The scalar field decouples from matter when the nonlinear term becomes large. If the nonlinear term is small, then Z is of the order 1, then the scalar field is coupled strongly, to matter. So what's happening is that you have a scalar field when it couples to itself, in the sense that the nonlinear term becomes very, very large, it couples so much to itself that it will decouple from the matter which is around. It is called a strong coupling in particle physics. This is something which is quite often seen in some theories. So when you have a field which is strongly coupled to itself, it decouples completely from the others. In some sense, it becomes so much egoist, it doesn't care about the others. So when the scalar field couples to itself that it has a lot of nonlinearities, in some way it decouples from matter. So that is actually this mechanism said in some generic way. I don't know if you have questions up to now. Okay, you looked all tired. More than me, actually. Maybe, I mean, I had something else, but maybe better not to force too much. And I will maybe just call Sushant, who will continue on now. Yeah.
So can you explain this process a bit more, like the strong coupling into a decoupler?
This process here, this one?
No, the strong coupling one, like when the scalar field.
Yes. So, yeah. So I was just rephrasing actually what I said here. The strong coupling means that the scalar field is strongly coupled to itself. So coupled to itself means that you have nonlinear terms like this. So then it has a coupling to itself which becomes extremely more important. And when you have this Z becomes very large, it decouples from matter completely, because that becomes 0 actually. So when a scalar field is coupled to itself strongly, it decouples from the other fields. So initially that scalar field is linked to all matter fields. And then it starts coupling principally to itself, it decouples from the others. That's the idea. So just to summarize it, we have seen two forms of mechanisms. When you have a scalar field, and there are many theories which do appear with a scalar field. Imagine that you have a Lagrangian, which is Einstein, and you have some scalar field. You have a kinetic term, you can have a potential, and you can have some nonlinear terms. There are two mechanisms, and you have the coupling to matter. One is related to the potential. This potential plus the potential which is coming from here gives a potential which has a shape which depends on the matter, and it's called a chameleon mechanism. If the potential is not there, you should look to the nonlinear terms. These nonlinear terms, they bring this strong coupling, and it makes that the scalar field decouples also from matter. So you have two screen mechanisms. This one also is the same. It tells us that if you are trying to make an experiment on Earth, you will never observe it. You have to go very far. Actually, it's a difficult thing to do to test that, but it has also some features, etc., and it can be tested. So Saturday, when I will make conclusions, I will just make a list of different experiments in the lab and things like that. It's showing what we have proved and disproved, what is working, what is not working, what theory is interesting and what it is not, actually. But tomorrow, we'll continue on another topic. Actually, it will be mostly GR tomorrow, because I don't think, it seems that it will be cut again. There is, I think, the Vice Chancellor who is coming. But the thing is that tomorrow, I will focus mostly on black holes, because so far I did mostly cosmology and some other aspects. but I will explain how do we calculate perturbations of black holes, how do we know stability of a black hole, and how do we calculate that the gravitational waves, they go at some speed. What is the speed of the gravitational waves? So in modified gravity, you can have gravitational waves which propagate, which is not at the speed of light, so then you will have some constraints. You can have some equation that will explain what is the quasi-normal modes, which are quite popular nowadays, and why they are interesting, and why and how to calculate them. So tomorrow it's going to be this. Mostly the calculation will be done in GR, and then I will generalize it, say how to do it, and you can do it easily then with Mathematica. But the formalism, we will see that tomorrow actually.